Good evening to you. Can you hear me? All right, so let us talk about causality in this session. So by the end of this session, you should be able to define and differentiate between different types of causal relationships, and then you will also be able to explain and apply the criteria for causal inference. You also be able to identify and assess the sources of bias and confounding in causal studies or in causal inferences. You'll be able to describe and use the different methods and tools for estimating causal effects, and then you also be able to evaluate and communicate evidence and uncertainty of causal effects. So those are the objectives of this session. So when we talk about causality, we are basically interested in understanding the relationship between an exposure and its effect, what we call outcome or health outcome, okay, in research, okay, which usually can be in an observational setting, but still can also be in an experimental setting. Okay, so what we are basically talking about is that you have a factor which can result into a disease, or which is linked to a disease. So we want to understand how that factor is linked to the disease, which is basically the health outcome or outcome basically. So that factor can be what we call a cause or an exposure. Okay, so we want to understand whether an exposure indeed causes or does not cause a given health outcome. Okay, so is it true that the factor we are investigating is that which resulted into the health outcome of interest? Or it could be that this relationship between the factor and the health outcome of interest is by chance, or because we did not collect the data in the right way. So therefore we have what you call bias. Or there is another factor which came in between and then distorted the relationship between the exposure and the outcome of interest. And that is what we call confounding variables. So those are things that we are that we are going to look at in this session. Okay. So we have already given the definition of causality. We said that with causality we are interested in understanding the relationship between a cause or an exposure and the health outcome that it causes. Okay, so we want to know whether a given factor, for example, uh, sex, is linked to the acquisition of a particular disease. Okay, so is there a causal relationship between uh, um, sex with a particular condition? So that is what causality is interested in. So this is very important in public health and in epidemiological research in particular, because we can be in position to identify the different risk factors that result into particular conditions, and therefore can be able to develop interventions to minimize or to remove the, the, the mentioned or the known risk factor. Okay, and then these interventions can be in terms of policies, in terms of decision making, and generally this contributes to the general knowledge of epidemiology in understanding how diseases occur in the population. Okay, so causality is very important because it allows us to know what risk factors are there and what health outcomes are they associated with, and to what extent are these risk factors associated with particular health outcomes, and which risk factors or exposures that we should actually give a lot of attention. So those are the issues that concern us when dealing with causality. So it is very important in public health because it forms the basis for us to design interventions to control diseases. So how do we determine, for example, how do we determine that it appears I'm not sharing the screen, right?
Yes, you're not sharing the screen, sir.
Sorry about that. I've just realized at the moment, but let me share that. Okay, so because I've not been sharing the screen, let me start from the start.
Okay.
Okay. So we are saying that we are going to talk about causality. And in this presentation, we should be able to know what causality is and how different factors can cause or contribute to diseases. And then how do we determine that certain factors can cause or can contribute to diseases. And when we do research on these factors and the diseases that they influence, what are the things that can distort the findings about these studies that we carry out? So, what are the tools or what approaches do we really use to determine causal effects? And then, how do you communicate evidence about uncertainty of causal effects? So that those are the objectives of this presentation. So when we talk about causal effects or causality, what we basically mean is that um, diseases have multiple factors that contribute to their occurrence. So let us say, for example, obesity. Um Obesity, which can result into complications related to the heart. and things to do with hypertension can happen because of obesity. So, how do we link obesity to cardiovascular conditions? Okay, so obesity is a risk factor for cardiovascular conditions. So how do we link that? What is the relationship between obesity, or let us say, what is the relationship between having high cholesterol uh, levels in blood in relation to having cardiovascular conditions? So that relationship between the risk factor, which we are calling the exposure, with the disease of interest, which in this case is the cardiovascular disease. What is this relationship? And how do we determine this relationship? Is it true that high cholesterol levels in blood can result into cardiovascular diseases? Okay, those are the questions we ask ourselves in causality. Why do we need to look at these factors? We should first acknowledge the fact that for a cardiovascular disease or for diseases to happen, there are multiple factors that are associated. So, for example, for cardiovascular disease, it could be the lifestyle, which may include smoking, drinking alcohol, and unhealthy diets. So all these are factors. So they are therefore risk factors, and they cause this disease here, which we call cardiovascular disease. So how do we design interventions to reduce cardiovascular disease? We can only do that if we know the conditions or the risk factors or the exposure responsible for cardiovascular disease. Okay, so that means that in public health it's very important that we know about these factors. What are those factors that contribute to disease? We don't want to deal with factors that do not contribute to disease. So we need to know these factors. So we need to know this relationship between these factors and the disease. So after knowing these risk factors, now we can design effective interventions to reduce the occurrence of these diseases in the population. And therefore, we have issues like designing public health policies, making decisions. You cannot make decisions out of the vacuum. You make decisions after getting knowledge, scientific knowledge about the relationship between exposures and outcomes. So that's why causality is very key. So how do we know that a given risk factor X is responsible for a disease Y? We usually follow two the criteria that we follow are two. One is what we call the Bradford Hill criteria, and then Koch's postulates. Those are the two methods that we can use to assess causality. So we are going to look at each of these in details. Bradford Hill is the name of a person. He was born in the UK, and he died, I think, around 1991, if I'm not mistaken. He was an epidemiologist. Okay, he was an epidemiologist and was actually a professor of medical statistics at the London School of Hygiene and Tropical Medicine. He used to work with Richard Dole, who was also well, a medical doctor working together with Bradford Hill. So Bradford Hill uh, created a criteria which has nine I can call them principles that have to be followed in determining causality. Okay, remember, we are saying that how do we know that factor Y is responsible for the disease X? Okay, that's the question we have. So for him, he said that look at these 9 things: strength of association, temporal relationship, dose response relationship, biological plausibility, coherence, analogous explanation, specificity, experiment, consistency. So those are the 9. So we are going to look at each of these. Okay, so strength. What does it mean? Strength means that, okay, if you increase, you're going to keep using y and x. Y is the factor, and then x is the disease. So with the principle of strength, it means that if you increase the exposure, which is y, if it is smoking, assuming y is smoking, if you increase y, the disease associated with smoking should all the number of people having the disease in which is in this case, let us say lung cancer, will also increase. So that means that if you take 10 cigarettes, your chances of having 10 cigarettes maybe in a week, your chances of getting lung cancer can, let us say, 10. If you increase the number of cigarettes you take to 20, also the chances that you have lung cancer may increase also, let us say, to 10%, from 5 to 10%. So that is one principle that has to be there. It means if the amount of exposure increases, the likelihood that you get the health outcome also increases. It means most likely smoking causes lung cancer. So that is what we call strength of association. Now let's move to the next one, which is consistency. Consistency is to do with the fact that the association between the exposure and the health outcome should be seen in different populations, in different settings, in different times. Even different researchers should find the same thing. So if we say that smoking is linked to lung cancer, we should be able to find that whether you do the study in the US, you should find the same thing. Whether you do it in South Sudan, you should find the same thing. Whether you do it whether you use what methods, whether you use the same researchers or different researchers, you should find the same thing. That's what we call consistency. If you find out that people who are staying in the US, when they smoke, they don't get lung cancer, then and when you come to Africa and then when they smoke and then they don't get maybe they get lung cancer, then there's likelihood that the exposure is not linked to the disease. I hope that is very clear. So you move to the third one, which is specificity. Okay? One exposure should be able to be associated with at least one specific health outcome. Okay? So for example, smoking is associated with lung cancer. But other conditions can happen. Uh, Other respiratory conditions can also happen, and their mechanisms can actually be um, uh, unknown. Okay, so what we are saying here is that the exposure should at least be associated with a specific outcome. So in this case, smoking, even if it linked to or commonly linked to lung cancer, still it can also result into other cancers, mouth cancer, throat cancer, whatever it is. But you can see that they're in the same kind of line. Okay, so that is very, very important in establishing causality. And then the fourth one, which is temporality, which is that the person should first be exposed before the disease happens. It does not happen in the other way around. That the person has the person who, still using an example of smoking and lung cancer, that the smoking must have been there before the lung cancer developed, not having the lung cancer and then followed by the smoking, and then you say that the smoking caused the lung cancer. The lung cancer was there um, by the time the person started smoking. The person had lung cancer, so you cannot say that the smoking was actually caused by the active smoking. I mean, the active smoking may not have been the cause. It's actually not the cause for the lung cancer, because the lung cancer was there before. So when we talk about temporality, we are talking about issues to do with time. What happened first? The exposure must have happened first before the disease. If the exposure comes after the disease, no, then it means that exposure is not the one which caused the disease. So we move to the next one, which is biological gradient. Okay, biological gradient is to do with the what we call the dose-response relationship between an exposure and the outcome of interest. The higher the exposure, the likelihood of the outcome. So if for example you have been exposed to microorganisms, maybe you have been exposed to a small cat, and then someone else gets exposed to a microorganisms through a big cat. The person who is exposed to microorganisms through a big cat is likely to develop the disease compared to you who has got a small cat. It's just like saying, if you get a needle prick, the chances of transmission of HIV through a needle prick cannot be compared to someone who has been transfused with the blood which is infected with HIV. The person who is being transfused with blood that is infected with HIV has high chances of getting HIV compared to you who has just got a needle prick. That is the point there. So this is to say that if someone is exposed to a larger dose of the exposure, the likelihood of the exposure of the health outcome will be higher. Okay, that is the point we are trying to emphasize there. So we move to the fifth one, which is plausibility. Plausibility, that there is the relationship between the exposure and the health outcome can be explained reasonably. There is something that is in science that we can use to explain the relationship between the exposure and the health outcome. Today I read about an article about people who got vaccinated with the COVID vaccine, there is an increase in reported, um, there is an increase in high high blood pressure. People are getting hypertension, okay, and they are associating that hypertension to COVID-19 vaccine. So the challenge is, the studies have indeed, some studies have indeed linked, not, I will not say linked, but some studies have been done to demonstrate that, yes, people who got the COVID-19 vaccine are reporting with high blood pressure, even without other risk factors for high blood pressure. So that means that COVID-19 is related to this high blood pressure. But is the COVID-19 vaccine the cause for the high blood pressure? We don't know. Is there any possible explanation for it? We don't know. But is it something that can happen? And if it is happening, can it be reasonably explained? At the moment, we don't know. Okay, so plausibility is that, okay, if you're saying organism A causes disease B, it is most likely that, yes, organism A interacts with the body in this way and it is able to cause an increase in high blood pressure through maybe increasing what we call peripheral resistance. Maybe. Okay? So with plausibility is that, can it be explained? Can it be explained? This is very important even in our real life. If things happen, if someone tells you something, you can either accept it or reject it on the principle that there is no logical explanation for what the person is saying. That is what we call plausibility. So sometimes, even if you don't know the answer, for example, if I ask you a question, and then you give me an answer which I did not expect you to give me. But when I reflect, I see that it is possible. So I will give you the marks because your explanation is believable, is understandable. There's a logical mechanism that leads to your answer that you're actually given. That is what we call plausibility. So we move to the next one, which is coherence. The association should be coherent with the existing knowledge and theory in the field and not contradict what is already known or what is already what we call established facts. Okay? That means this does not create room for explanations that, or for situations that are not usual. There are things that we already know. For example, we know that Mycobacterium tuberculosis is responsible for the disease TB. That is what is known. Now, if you do another investigation, it is very hard for it to be contrary to what is already known. It is very hard for people to believe you because this is what is actually known. So don't create contradictory statements. Okay, so if TB is caused by bacteria, don't wake up tomorrow and tell us it's caused by a protozoa. When you say it is caused by a protozoa, that is completely out of the question because what we really know by fact is that tuberculosis is caused by a mycobacteria. So that is to say that your findings should be coherent. Then we come to the ninth principle, which is experiment. Is that you can confirm whether a disease A causes or is caused by a factor B. You can confirm that by an experiment. So you can conduct what we call an experimental study. That will give you the proof of that the exposure is associated with the given health outcome. Okay? Then we move to what we call analogy. It's the last principle. Analogy is on the fact that the association should be similar to the other non-causal relationship in different domains or contexts. Okay? If you, for example, let us say, you say that a given factor causes a person to lose, let us say, a given factor X causes a person to have anemia. And therefore, you can still reproduce this same relationship even in other situations. For example, if you test it in rats, you can be able to find the same thing, or even another species. Okay? So you still get the same relationship, whether you use the same format, or the same format of exposure, of form of exposure, or another different form of exposure, whether you use different animals, it should be the same. That is what you call analogy. Okay? So that is the Bradford Hill criteria. Do we have any questions so far? Do we have any questions so far? Okay, so we move forward. The next criteria we said is Koch's postulates. Koch was a German physician and microbiologist. He helped in establishing a criteria that can be used to establish causal relationships between a microorganism and the disease. He's the one who actually identified that tuberculosis is caused by a Mycobacterium tuberculosis. So it is Robert Koch who identified that. So what does he really say? What does he really say? He says the following, that the microorganism should be present in abundance in all organisms suffering from the disease, but should not be found in organisms that are healthy. Okay? This is to say that if you say that Mycobacterium tuberculosis causes TB, it means that people who have TB should be having Mycobacterium tuberculosis, and people who don't have TB should not be having Mycobacterium tuberculosis. So that is one thing. The second thing is that you should actually be able to get that microbacterium and isolate it and actually be able to grow it in culture, what we call culture. So if you get the sputum of the person, then you culture it, you should be able to see the Mycobacterium tuberculosis. So that is the second point. Okay, so if you get that the microbacteria that has been grown in the culture and you introduce that into a healthy organism, the disease must be the disease, which is in this case Mycobacterium tuberculosis, should be able to happen. Okay, so that means that you can be able to have the experimental host diseased and should be able to get the condition which is similar to what you got from the diseased organism. That's what he says. Okay. So we apply Koch's postulates in infectious conditions such as tuberculosis, cholera, anthrax, and leprosy. Okay, so basically what he says is that if you're saying that an organism X causes a disease Y, that means that for all people who have the disease Y, they should have X. But people who don't have the disease Y should not be having X. That's what postulate says. It is very good at explaining diseases caused by microorganisms, but we cannot use his postulate to explain diseases caused by environmental toxins and also diseases caused by mutations, because we cannot culture them, we cannot isolate them and then be able to see. Okay, so we usually use it in infectious diseases only. Okay. Still, I pause here and ask if we have any questions so far.
It's okay. We can continue.
All right. Good. So we usually we usually use the criteria that we have explained to be able to really determine these relationships. And sometimes, for example, when COVID came, there were very many issues put across as the causes of COVID. Okay, but if we know these criteria that we have explained, then there are some things that we can be able to eliminate and say no, it does not. The COVID-19 did not happen like that, or COVID-19 is not caused by this. So it helps in us in making decisions on what causes what and under what situations. Can it be explained or not? Is what we are saying something that is real or it is happening by chance? Okay, those are things that we really need to ask ourselves about. Now, the next phase of our discussion is going to be on what we call methods for assessing causality, or what just basically you can just say research or epidemiological research designs that can be used for assessing causality. Okay, that's what basically we are going to look at. This is to say that you actually don't know the relationship between the exposure and the disease, but you want to investigate that relationship yourself. So it means you're going to carry out the research yourself. So you need to design good research studies to establish that. Often we use what we call experimental studies, okay, or what we call randomized control trials. There's someone with a hand up. Yes, Dennis. Tokwaro, your hand was up.
No, it's okay now. You went off for some seconds. That's why you see others were leaving also and rejoining.
Oh,
But now I'm getting you.
okay. All right. So you need to design a very good study. Don't have what we call confounding factors disrupting your investigation between the exposure and the health outcome. You're going to look at all these, the confounding factors, and how you can take control of them. Okay? So that is where we are. Okay? Now, before we actually go to those research designs, let's first look at what really happens between the exposure and the health outcomes of interest. What are those relations? So, for example, you can have an exposure Y that causes a disease Z directly. But you can have an exposure Y that results into a disease Z through another factor in between X. So you have Y acting through X to cause Z. So that means that X is an intermediate factor, which we call in this case an intermediate variable. Hope you have understood that. So we can also have Y causing Z, but in between there are factors such as X and then W. You have multiple intermediate factors before you have the health outcome Z. So basically, this is what we say about what we call a causal pathway. So let us say the outcome of interest is a road traffic accident. Okay? Now you have many factors that can happen that can result into this road traffic accident to happen. So one, you could have a person who is not trained in driving, and then he drives at a very high speed, and then let us say there are no traffic or road signs. So you see that the person does not know how to drive and may cause an accident, but there are other factors in between. Maybe he was drunk, and also there was no road signage, and then the accident happens. So that path from lack of driving skills, one, to driving when you are drunk is another factor, and then leading to lack when also there are no road signs, and then the accident happening. Okay, so that is what we call the causal pathway. So for a disease to happen, for example, diabetes, you will have poor diet, genetic predisposition, lack of exercise, and things like that. So all the things will combine until they lead to the health outcome of interest. Then you can have other variables or other exposures that happen and may lead to the health outcome of interest, and it can be observed, but the relationship is not actually causing the problem. Okay? So there is what we call the non-causal relationship, or the relationship is not causal. I hope you understand that. Yeah, it is very clear for you to really note it. Okay? You can have what we call a causal relationship, which has to be met by the Bradford Hill criteria that we talked about, and also maybe by the Koch postulates. But you can also have other factors that may result into a given health outcome, but those factors are not actually causing it. This is now where you need to know what is called association and causation. Association is not causation. Association is not causation. This is what you really need to know. So you can have other factors that are associated with the health outcome, but they are not actually causing the health outcome. Now this is where now you come to some of these factors that may, for example, the confounding. When you talk about a confounding factor, for you, your interest is to see that is it true that lung cancer happens when someone smokes? So for your interest is between smoking and lung cancer. But there could be another factor that can result into lung cancer and you have not really looked at it. And that is the third factor, which we call confounding variable. Which we call a confounding variable. So please know what a confounding factor is. So don't carry out an investigation and forget that there are other factors which can influence the health outcome of interest. For you can be linking smoking to lung cancer, but there could be another factor, for example, environmental pollution, or for example, genetic predisposition, or for example, exposure to occupational hazards like asbestos. This can cause lung cancer, but for your interest is only looking at smoking and lung cancer. And yet there are other. It's just like when someone comes and steals from you. You may be focused on one person, yet there are also possibilities that another person would have actually been the one who stole from you. That's what we call confounding. And then there is what we call mediation, which is basically what we had explained, that a disease A happens because of an exposure B. But there could be another variable in between that can also lead to the health outcome of interest. So that the one which is in between is what we call the intermediate variable. Okay? So you just need also to know that you have these exposures interacting with one another. If you smoke and then you work in a mine where you're exposed to toxins, this smoke and these toxins from your workplace, I think they're going to interact. So they may result into worse health outcomes. So exposures do interact. They can result into what we call synergistic interactions. If you watch the video that we had during the day, you must have known that additive interaction or synergistic interactions or antagonistic interactions can have them. Okay, now having looked at how these exposures interact with one another, now we can look at the research designs that we can use to establish causality. So the first, but before we go to look at the first, you need to know that establishing causality can be done through what we call analytical research designs. Remember, we have two major types of designs. The classification can vary, but we can have what we call descriptive research designs and then analytical research designs. Or if you remember the presentation on epidemiology, we have two types of epidemiology, or two types of epidemiological approaches: descriptive epidemiology and analytical epidemiology. Descriptive epidemiology, you are basically interested in knowing who, where, and when. Who is suffering from what disease and when do they suffer from it? So the studies that can be done there are the observational studies. For example, cross-sectional studies, or what we call prevalence studies. You're basically interested in knowing who is suffering from what and when. But with analytical studies, you're interested in why and how. Why is it that these people are the ones getting the disease, and how do they get it? So the analytical research designs are the experimental studies, which in most cases are the randomized control trials, cohort studies, and then case control studies. And those are the ones we are going to focus on. So the randomized control trials are very unique. One is that they are experimental, or what you call interventional studies, where, of course, the experimenter or the researcher manipulates the environment or the exposure and then investigates the outcome of interest. Key things that have to happen. One is what we call randomization, where in your study you have two groups: the intervention group and the control group. So for example, you're saying that an organism A causes a disease B. So you want to test whether indeed, if you inject people, let us say in this case animals, with organism A, they will actually get the disease B. And then, so the ones you are going to inject are the ones we call the intervention group, or the experimental group, or the interventional group. The ones that you're not going to inject are the ones we call the control group. So those that you inject, then you see if they're going to get the disease or what can be. And then those that you did not inject with the organism A, they will not get the disease B. Okay? So when you do this, that is what you call an experimental study, because you are the one manipulating the what? The exposure. But the groups of the individuals who go to either the control group or the intervention group, they have to be assigned to those groups randomly. So random assignment is very important. That's why we call them randomized control trials. So we often use what we call double-blind randomization, where the people who are receiving the organism A do not know whether they actually received it. Even those in the control do not know whether they actually received it. Even the researchers don't know whether they administered A or something else, or a placebo. So that is very important because it takes care of biases and also minimizes what we call confounding. The challenge is that it takes a lot of resources, it takes a lot of time, and sometimes you don't want to inject people with organisms that can cause disease. So that raises unethical issues. And you don't want to be involved in that. So sometimes it is not possible to do it all the time. So we end up with the other studies which we call the observation, which include the cohort and the case control. Here you don't really manipulate. Okay, with cohort studies, you follow up people over a given period of time to see if they develop the disease of interest. Okay, so for example, you get records of people who are smoking, and then you get people who are not smoking, and then you follow them for 10 years. How many of these people in these two groups will develop the disease of interest? So when you do that, when you follow people up and then see what happens, that is a cohort. But if you also follow up people, okay, and compare them with those who don't have the disease of interest, then we have what you call case control. Okay, this is to say that you have a person who is exposed, and then you get a person who is not exposed, and then examine the health outcome of interest and see if there is a relationship. Okay, so you do calculations that we call measures of association that I think you will have to look at in our presentations. In epidemiology, you have that lecture for measures of association. They are related to what we call case controls studies. So if you have people who are having a disease Y, and then those who don't have, and then calculate the chances of them getting a disease of interest, then you can be able to note whether there is a relationship between the exposure and the health outcome of interest. So you can do that through calculations of measures of association. So that is for case control studies. If I can repeat, with case control studies, you do it for people who have diseases which are very rare. Okay, so you have maybe 5 people who have a disease that you're interested in. So those people are the ones we call the cases. And then you get other 5 people who don't have the disease. We call them the controls. And then look at their exposures. Okay? You'll find out that the people who are the cases may be exposed to a particular exposure compared to the controls, and therefore you can be able to link the disease to that exposure through carrying out what the calculations we talked about, which we call the measures of association. Now we have understood that you can carry out those studies, the experimental studies, the cohort studies, and then the case control studies. But remember what we have just said, that experimental studies can always give us the best evidence that we are looking for. But in most cases, we cannot be able to do them because of time and cost. So we resort to other studies, like the case control and the cohort studies. But regardless of the type of study that we are going to investigate, the type of study that we are going to use to investigate the exposure and the health outcome, there could always be issues to do with biases or with weaknesses, or there are things that might not have been done correctly. So you need to evaluate the findings from these different study designs. So you need to evaluate and determine whether you can actually apply all the findings or you cannot apply those findings. So that means that for you to use any of the research study designs, you must have carefully evaluated the strength and limitation of each of the study designs. Okay, so in our presentations, you have seen that we have pointed out some limitations. Here, limitations, and also limitations there. So it means that in your decision to choose which design to use, you need to look at the limitations that you have, the nature of the research question, whether you can really be able to do it. Is it feasible? Is it practical? What are the potential issues that you will have in terms of the ethical standpoint? Okay? But overall, you want to do something that actually gives good evidence. The association measures that I kept talking about are the ones that help you to really see that if you smoke, you have 15% chances of getting lung cancer. So that 15% chance is what we call the measures of association. So we have majorly two measures are used: the risk ratios and the odds ratios. But you can also have hazard ratios. And these are the ones I say you should look out for in one of the presentations we have had. Okay, so I think let's end here for this presentation.